Welcome back. So, as with the polynomial inequalities, rational inequalities can be solved purely algebraically as well. Now, the trick with these and the procedure is outlined on page 686. I'll ask you to follow along. It's quite wordy, so I will not reproduce it here. But what we want to do is get one side equal to 0 to begin with. So with this inequality, I would maybe move the 5 over 3x plus 1 over to the other side by subtracting it. From both sides. So my inequality then becomes x over 2, or x minus 2 over 3x plus 1 minus 5 over 3x plus 1 is less than 0. Alright, now I see that I actually have a common denominator. So this is not quite in standard form yet. I would like it better if this were one rational function on the left. So since I do have a common denominator, I can combine this x minus 2 minus 5 over 3x plus 1. Now, if I did not have a common denominator, I would need to supply one. I would need to reduce this down, turn it into a single rational quotient. Alright, so simplifying just a little bit further, this is actually x minus 7 over 3x plus 1 is less than 0. So we could then graph this rational function on the left. But we have a slightly shorter way of doing things. So we want to find the zeros of the numerator, p of x, in this case x minus 7, and of the denominator, q of x, which in this case is 3x plus 1. Now those zeros are critical numbers. The zeros of the numerator are zeros of the whole function. You can verify that once we find them. And the zeros of the denominator, we saw in the last section, are either wholes or vertical asymptotes. Now our function, as we saw in the last problem, our rational functions can change their sign. They can go from being negative to positive or vice versa at their x-intercepts or at their asymptotes, right? 1 over x is negative to the left of its asymptote, and it's positive to the right of its asymptote. So that break in the function allows for it to change its sign. So we want to find all these zeros, because those are all of the places where our function will have to, or potentially might, change sign. Everywhere else, it's going to stay either positive or negative. So in the intervals in between, that's where our function behaves nicely. Doesn't go changing its spots on us. So let's find those zeros. Zeros of p of x, if 0 equals x minus 7, then x equals 7. And of q of x, if 0 equals 3x plus 1, then negative 1 equals 3x, so x equals negative 1/3. So if we plot both of those on the number line, negative 1/3 being the first that we'll encounter, and 7 after that, then we are going to do the exact same procedure we did for polynomials. We are going to figure out what is the sign of our function x minus 7 over 3x plus 1. Now this rational function is actually kind of nice, right? If I pick an x value below negative 1/3, less than negative 1/3, say negative 1, that's a nice easy number to plug in, my function would be negative 1 minus 7 over 3 times negative 1 plus 1. So that's a negative in the numerator and a negative in the denominator for a grand total of positive. Now we don't really like positive, we are shooting for negatives. So we don't like that one. Then what's going on in between negative 1/3 and 7? Well, 0 is a good x value to plug in. So if we plug 0 in, 0 minus 7 over 3 times 0 plus 1, that's negative 7 over positive 1. So a negative over a positive, that is negative. And we like negative, that's what we're going for. So last, we want to plug in something past 7. I think 8 might be a good choice. So 8 minus 7 over 3 times 8 plus 1. So we have a positive over a positive. Now how much each of these is doesn't particularly matter. We only care about the signs. So positive over positive is positive, which means that the only interval that worked was between negative 3 and 7. Now, the question is, do I want to include the endpoints? Well, the endpoint of 1/3, negative 1/3, came from the denominator. That was a 0 of the denominator, so this is never going to be a solution. And in fact, no zeros of the denominator are ever going to be part of the solution to these inequalities. They're not allowed to be plugged in at all. So they definitely can't satisfy our inequality because not in the domain. And I will contend that 7 is not part of the solution because our inequality is strict. So 7, if you plug 7 into this inequality that we're trying to satisfy, is 7 minus 7 over 3 times 7 plus 1 less than 0? I would say not, because our numerator is 0 and 0 is not less than 0. So that is not a good one either. So both of the endpoints should be excluded, and our interval of interest is negative 1/3 up to 7. So any x value you choose out of that interval will satisfy our original stated inequality.